Okay, so we're going to take a look at these energy versus position graphs for different objects as they're moving. So right now the bulldog has purely potential energy gravitational, and as the bulldog moves down the ramp, it converts that energy from potential energy gravitational to kinetic energy of motion. So as we watch the bulldog, and let's speed it up just a tad. So we'll just watch it to halfway. So you can look at this energy versus position graph. So the green line is showing us the kinetic energy, and the blue line is showing us the potential energy. So at the very beginning, position 0, so 0 position would be at the top of the ramp, the bulldog has purely potential energy gravitational. And as the bulldog's moving down the ramp, it's losing gravitational potential energy and it's gaining kinetic energy. So right about halfway, we can see that the bulldog has half potential energy gravitational and half kinetic energy gravitational. But at any given point in time, the total energy remains the same. So if we add these up, if we take a look at position 2 meters, we'll see that the bulldog has 250 joules kinetic energy and 750 joules potential energy, adding to a total of 1,000 joules. Same thing goes for position 0 meters. Position 0 meters, the bulldog has 0 kinetic energy, 1,000 joules potential energy. So no matter what, at any given point in the position, the total adds up to this 1,000. So as we keep going, we can kind of predict what this graph is going to look like for the remainder of this distance. That green line should continue going straight up to the top because the bulldog will have only kinetic energy at the very bottom and no potential energy, gravitational. And that blue one will go straight down to the bottom. So let's see. All right, there it is. So at any given point in this position, the blue line, the height of this blue line plus the height of the green line adds to the total, meaning that total mechanical energy is conserved. Potential energy plus kinetic energy is going to equal the total no matter what. Okay, let's take a look at another example of this energy versus position graphs. So in this second example, we can see that the ramp is shaped a little bit differently. It kind of has a curve to it. So we can expect the bulldog to have a gain speed really quickly here, but then as it increases speed as it continues, since it's not as steep of a slope, it's not going to be increasing in speed as quickly as it were up here. So when we look at our energy versus position graph, we notice that as the bulldog moves down, it should be losing potential energy and gaining kinetic energy. So far in the graph, if we look here, the kinetic energy is increasing rapidly and the potential energy is also decreasing rapidly at the same exact rate. And at any given point in this position, so at position, it looks like about 1.1 meters or so, half of the total energy is potential energy and half the total energy is kinetic energy. About 50, I don't know, I would say that's about 550 joules of each. Okay. So then if we continue down the ramp, we'll notice that the potential energy graph looks a whole lot like the actual motion that the dog had, because that is the height relative to the ground, and the kinetic energy is the inverse of it. All right, let's take a look one more. Okay, for this third example, we have a U-shaped ramp, and we know for sure that the bulldog has purely potential energy gravitational up at the top, and that the bulldog is gaining kinetic energy as it approaches the bottom of the ramp. But we should see that it doesn't gain, it still has potential energy gravitational at the bottom of the ramp, because relative to our reference point, if we look right here, our reference point of 0, our height of 0, is further below the bottom of the ramp. So actually the bulldog should have some gravitational potential energy at the bottom of the ramp as well as its kinetic energy. It is moving the fastest at the bottom of the ramp throughout its entire path. And so let's take a look at the energy versus position graph. Okay, so for the energy versus position graph, as the bulldog goes down the ramp, it is losing potential energy gravitational, and it's gaining kinetic energy. However, at the bottom of the ramp, just as we predicted, it still has some potential energy gravitational because it's not at a height of 0. But at that exact point, it looks like about 250 joules of potential energy and about 1,000 joules of kinetic energy, adding to a total of 1,250 about for the total. So same thing over here at position, looks like about 1.5 meters. Right here, the bulldog has about probably 625 joules of kinetic energy, and then 625 or so of potential energy gravitational, which adds to our total, once again, 1,250. So at any given position, if you add that y-coordinate of the blue line plus the y-coordinate of the green line, you'll get the y-coordinate of the total energy. So that's something to consider when looking at these graphs. Okay, so we're going to take a look at a couple examples of these energy position graphs. As soon as you start to feel like you understand it, you should pause the video and try it before you actually see me explain it. So in this example number 1, we can see the total mechanical energy is shown here in the red line, and the potential energy gravitational is shown here in the blue line. And we are gaining potential energy gravitational, so that must mean for our kinetic energy, we must be losing kinetic energy. If we have 0 potential energy, we must have full kinetic energy at the beginning. And at the end, if we have full potential energy, we must have 0 kinetic energy. So our line is going to start here and go through here. So it looks something like this, like any given point. So if we were to add the y-coordinate of this blue line right here plus the y-coordinate of this green, it equals this red total. The total mechanical energy is always a perfectly horizontal line. All right, here's another example. In this case, our potential energy gravitational is not quite as steep. So at the end, we don't have purely potential energy. It doesn't go all the way up to the total mechanical energy line. So if we were to think in terms of numbers, let's say that the total mechanical energy were 20 joules up here. Well, potential energy is about halfway, so I would say that's about 10 joules. So that means at this exact point, for potential energy is 10 joules, that must mean kinetic energy must be 10 joules. Same thing for the beginning. If this is at 0, that means we have 0 joules of potential energy. So to fulfill this total being true, we have to have 20 joules of kinetic. So our line would look something like that. So you can always put numbers to your graph if you need to understand it a little bit better. So at this point, if you want to try this example number 3 on your own, before I explain it, please pause the video, draw it, and then predict your kinetic energy. Okay, so now that you made a prediction, if we have half potential energy throughout the entire, from 0 position to however far we've moved, that must mean we have half kinetic energy the entire time also. So if we think of in terms of numbers, if this is 20 joules of total energy, potential energy is 10, that must mean our other 10 must be kinetic energy throughout the entire time, or throughout the entire position. So that's what our kinetic energy graph would look like. So if you drew a line right on top of your potential energy graph, that is correct. Okay, for this example, we can see that we have a constant potential energy here, and then we lose potential energy. More than likely, we should be gaining kinetic energy in this moment right here. And then we have a constant potential energy again. But the key here is that our kinetic energy has to add with our potential energy to be our total. So if we think in terms of numbers again, this looks about halfway in the graph. So let's say that's 10, and this is 20. This looks about 3/4 of the way, so it's about 15 joules. That means if we have 15 joules potential energy and 20 total, we must have 5. So our kinetic energy is going to be about right here. So our kinetic energy is about 5 here, and then it increases to the 15, because 15 for our kinetic energy plus 5 of potential would add to our 20. And remember, I'm just using numbers just to make the graph make a little bit more sense, but there is no need to use numbers if you don't need to. All right, so go ahead and try example 5 on your own and then check out the answer. So we have pure potential energy here, and we are losing potential energy at this rate that you see here. It's not a linear rate. So that must mean we must be increasing in kinetic energy at the inverse of whatever we lost our potential energy. So if you predicted your kinetic energy to look something like this, that is correct. And if you check your work at any given position, if we add that y coordinate plus this y coordinate, we get whatever this is. And you can actually use a ruler and measure this distance to the x-axis plus this distance from the blue graph to the x-axis. That should equal the total distance from the red line to the x-axis.